Um, Thomas, are you going to do the introduction or
That's
should
fine.
I?
I would do it. Yeah.
Okay.
Okay. So welcome everybody to the NCG and T seminar in Prague. It's our pleasure that this day we have Satyajit Guin, who is going to talk about the holomorphic geometry on the quantum projective line. Please.
Thanks, Thomas. So, first of all, I'd like to thank the organizers for inviting me to give a talk. So, I'll be talking mostly CPQ1, but recent developments, kind of last October onwards. So, let me quickly go through the preliminary setup, starting from SUQ2 onwards. So we have this coordinate algebra of the compact quantum group SUQ2 generated by two generators. So I'm fixing the notation by A and C. And the relations are, these are well known. The relations are you demand this matrix U to become unitary. And it has the Hopf algebra structure given by this antipode, coproduct antipode and the co-unit by this formula. So on the dual side, we have the quantized universal enveloping algebra of the Lie algebra SU2. So this is again a Hofstad algebra, which is generated by three generators EFK. Well, actually four, EFK and K inverse, satisfying certain relations. And then again, we have the Hofstad algebra structure specified by this coproduct, antipode, and co-unit by these formulas. So what is important here is that there is a non-degenerate bilinear pairing between these two Hopf algebras. So I can view this UQ-SU2 inside the linear dual of coordinate algebra of SUQ2, which allows me, so this is the dual pairing is specified by these relations on the generators and all the other pairings are zero. So this viewing this inside the dual allows me to specify the action of the UQSU2 on ASUQ2 by this formula left and right action. So these are both this action left and right in this particular case, they are mutually commuting. So meaning it doesn't matter whether you first do the left and then right or first right then left. And these are uniquely fixed by this relation. So now comes the main topic, our Podle sphere, which is the underlying smooth manifold one can think of inside CPQ of the CPQ1. So how is it obtained? So you have first considered the Hopf algebra homomorphism from SUQ2 to circle given by this formula. You send A to Z and C to 0. And then the standard Podle sphere is precisely set of all elements in SUQ2 which satisfies this rho x equal to x tensor 1, or otherwise you can view it as directly by the generator relation prescription, which is two generators are there, B0, B plus, and another one B minus, but which is star of the B plus. So two generators, B0, B plus, and satisfying these three relations. So this is the standard Podle sphere, which is obtained out of SUQ2 via the homomorphism rho. So now here we can encompass the UQ-SU2 action here on the SUQ2 to obtain this weights-based decomposition. So this is the linear direct sum of the coordinate algebra SUQ2 in terms of all these lns. So which are this weight space? This capital K is the coming from the UQ-SU2. I have the left action. So look at the left action by capital K equal to Q to the power n by 2. This is the weight. So obviously if n is 0, so then you realize that this is the kind of the fixed point under the capital K action, which is equal to the standard Podle sphere, SQ2. Okay, so what happens extra is that, not extra, I mean more structure is that all these lns, they become coordinate algebra of the Podle sphere by, so let me just simply say Podle sphere. It is understood that I am talking about the coordinate algebra. So let me just simply say SQ2. So all these lns, they are SQ2 by modules. Not only that, they are finitely generated projective left SQ2 modules also. So that means in all these LNs, they are basically vector bundles over the codeless sphere, which are analogous to this canonical line bundle. So SQ2 Qs are in between 0 and 1. So at the limit Q equal to 1, we recover this Riemann sphere. So there we have the canonical line bundles ON, and these LNs match with O minus n of degree minus n. So these are the quantum line bundles over the codeless sphere. So now to encompass this is the smooth setting. To encompass the complex set structure, so first we need to specify what is the differential calculus on this codeless sphere. So this is the standard one coming from the restricting the Warnowitz's, the 3D calculus of SU on SUQ2. So you have two generators x minus and x plus on the tangent space level, which are specified by this formula q power minus half fk and q power half ek, corresponding dual left invariant forms in the dual side one forms. These are omega minus omega plus. If you specify like this, then what happens? The differential df you can decompose into two parts. One is using this x minus action, and another one is this x plus action. So this is precisely the holomorphic and anti-holomorphic decomposition of the differential D, where this del bar f is the anti-holomorphic differential and del f is the holomorphic differential by this formula. So this allows me to decompose this space of one form into two separate chunks, 0, 1 and 1, 0. So what happens, this 0, 1 space that becomes back to bimodule isomorphic with the L minus 2, and the 1, 0 space that becomes isomorphic with L2. And both of these are finitely generated projective, as we have already said, and these are in particular rank 1. And the space of two forms, that is a free module of rank 1. It's just the algebra SQ2 itself. So in other words, so now this is the full differential calculus of the standard codeless sphere. So at the 0 level, we have the algebra itself, ASQ2. The one form gets decomposed into holomorphic and anti-holomorphic part, where L minus 2 is the anti-0, 1 part, L2 is the 1, 0 part. And the two form has only this ASQ2 element, the free module of rank 1. So that is basically omega 1, 1 you can view of. Omega 2, 0 and omega 0, 2, they don't exist, they are 0. So these are the corresponding differential from 0 level to first level and the first level to the second level. These two are the precise formula for the differential. So now with this complex structure, we can say that CPQ1 is precisely the standard codeless sphere equipped with this differential calculus, which implements the complex structure on the standard codeless sphere. So henceforth, we'll be saying only CPQ1 to mean the coordinate algebra itself. Okay, so the underlying smooth level, this is the standard codeless sphere. Okay. So one remark here is that the above differential calculus you can also view in terms of the Dirac operator, which was constructed way back in 2004 by Smutgen and Wagner. So that associated cone differential graded algebra you can visualize as this the calculus which was prescribed above. So just we'll come back to this Dirac operator prescription in a moment. So that time I will specify in detail. Okay, so now we have the complex manifold CPQ1. What are the vector bundles in our? So we'll be speaking to vector bundles means left module and connection means left connection. So vector bundles are finitely generated projective left modules over the ACPQ1. And this is called holomorphic vector bundle if additionally it admits a del bar connection, 0, 1 connection. So in this case, what happens is that this omega 0, 2 does not exist due to this dimension constraint that we are working on CPQ1. So every del bar connection is automatically flat. So flatness one doesn't have to check. So that comes automatic. So holomorphic vector bundle over CPQ1 simply means it's a pair which consisting of a finitely generated projective left module and a Delbar connection on it. So these are all holomorphic vector bundles. Now this is the 2011 introductory paper due to Khalkhali, Landy, and Swilecombe. So they constructed the holomorphic structure on the line bundles ln. So by that, what we need? We need to specify some Delbar connection on each ln. And this is the precise formula from this phi going to this prescription, where x minus was the f action, basically f left action, because k left action has no role because the SQ2 is essentially the k fixed point algebra. So k does not play any role. Only the f action plays the role. So by using that, they have constructed this holomorphic structure on the ln, each line bundle. And we'll be calling this a standard holomorphic structure for obvious reason, because we are essentially going to see there are many non-standard. So in particular, they have also computed the associated cohomology space. So these are for the positive side, these are 0, but for negative side, this cohomology space dimensions are keep on increasing as n is approaching towards minus infinity. So in particular, if you take n equal to 0, this is the line bundle L0, which is nothing but CPQ1, the underlying algebra of the coordinate algebra of CPQ1. So there, the standard holomorphic structure is nothing but the Delbar, original anti-holomorphic differential Delbar. And if you look at the associated, this quotient complex, that reduces to this Dolbeau complex. So it has only two terms. The first term is the L0 and the second term is omega 01. Apart from that, nothing else survives due to, again, dimensional constraint. So what happens? This first place, the 0, place, the kernel Delbar is the C, but in the 0, place, the cohomology becomes 0. That was computed first, I think, up to the best of my knowledge, by DeAndre and Landy in 2013. This is the paper Geometry on Quantum Homogeneous Spaces. So they have computed this cohomology to be 0. So what does it say? That because this Delbar is now this 0, position, the Delbar is surjective. So this cohomology 0 in particular tells you that this map, Delbar from the CPQ1 to L-2, this is a surjective map. So this is a special feature of CPQ1. We are going to use this later. Okay, so now let me quickly describe. One holomorphic structure is there on each ln, which we are calling standard. How does all the holomorphic structure look like? So that is not difficult to visualize, because it is known that difference between two connection is essentially alinear. So we are going to use that fact. So in the CPQ1 setting, what happens here is that there is a precise bimodule isomorphism between these spaces. So this is basically, that means you can flip the position of the ln with respect to this 0, form. So that is what it is saying. Now, in using this twisted flip isomorphism, what one can observe that all holomorphic structures are of this form. So they correspond to elements of the coordinate algebra, Delbar F. Because Delbar is surjective, all the elements of the omega 01 is going to look like Delbar F. So that's why only Delbar F appears here. So all holomorphic structures, N stands for ln, and this Delbar F, F is varying over the coordinate algebra of CPQ1. They look like this. Where this Delbar N 0, we are denoting this standard structure constructed by Khalkhali et al. By this Delbar N 0. Okay. And phi n was that flip isomorphism. Fine. Now let me mention, and this is the correct place to mention. So if you look at the classical situation of Riemann sphere, what happens there? That every holomorphic vector bundle decomposes essentially uniquely up to permutation. So it decomposes into line bundles, ONs, several copies of ONs. So is it true for the CPQN? So for that, first, one has to understand the line bundles over the CPQ1, but that itself is now difficult. I mean, difficulty level has increased due to this discovery in last October 2025. So this group of 5 people, Grebman and Jouting is going to speak, of course, after this. So he's one of the author. So what they have constructed is essentially more than one holomorphic structure on LN. Now, this is a purely quantum thing. So if you look at classically Riemann sphere, the line bundles have unique holomorphic structure. So this is no longer the case over the CPQ1. So for that, what essentially we need to investigate is the gaze equation. So you pick 2 holomorphic structure on LN. So they look like corresponding to del bar F1 and del bar F2. F1, F2 are varying over the CPQ1, the coordinate algebra. Then one can realize the gaze equation takes this form, this del bar G equal to G del bar F1. So where question is whether these holomorphic structures are gaze equivalent or not is essentially solving this gaze equation for some invertible element in the sister algebra associated with the coordinate sphere or CPQ1. So this solving what just let me mention the name. So if you are taking F2 to be 0, I will call it gaze equation only for F1 if F1 is there only. Otherwise, I will call it mixed gaze if both the F1 and F2 are present there. Now, this is what I was saying that classically, if you look at the Riemann sphere, what happens on the line bundles when you have the unique holomorphic structure? That is because the gaze equation always admits a solution. You have the exponential function classically. So all the whatever holomorphic structure you take, that will be isomorphic to the standard one. Isomorphic in the sense gaze equivalent to the standard one. So you have unique structure. Now in October 2005, these 5 people, Grebman and Jouting and 3 more. So they are saying that there are many holomorphic structure on each LN. So not only that, it's a surprising thing that this, if you look at the space of holomorphic sections, so which is the kernel of the holomorphic structure, the connection del bar. So that space dimension is keep on increasing indefinitely. Whatever you take any natural number, they have produced existence of some non-standard structure such that the space of holomorphic section has dimension exactly equal to that natural number. So that means this space is increasing. The dimension is increasing. So they are essentially, so I'll be briefly mentioning their result because anyway, Jouting is going to speak later. So what they have essentially looked at, you have 2 generators of the coordinate sphere, B0 and B+. Among them, B0 is self-adjoint. So you look at the sister algebra of the standard coordinate sphere. This B0 spectrum, the self-adjoint B0 spectrum, that is very nice. It's a Q to the power 2n only, including 0. So what you can do, if you look at the sister subalgebra generated by B0, that becomes commutative. So you can apply the continuous functional calculus to identify it with the functions on the spectrum of B0. Now what happens, the holomorphic, anti-holomorphic differential del bar, if you restrict to this particular subalgebra, it looks very nice. It is essentially given in terms of this Q differential, this Jackson's Q derivative. So they have looked at this sister subalgebra generated by B0. Now you look at inside the coordinate algebra, so which essentially boils down to looking at polynomials in the B0. If you pick your functions from that particular subalgebra, then they have constructed infinitely many such functions for which the corresponding holomorphic structures are not gaze equivalent. So there are no invertible elements for which you can solve the gaze equation. But one has to notice one fact here that their analysis is crucially depends on this continuous functional calculus. So you cannot go beyond this particular subalgebra. That method will fail simply because functional calculus is no longer there. So natural question. So they are saying there are infinitely many, countably infinitely many distinct structure on each line bundle ln. Natural question is whether these are all. So why that question appears? Because they are looking at a particular subalgebra, not the full coordinate algebra of CPQ1. So there is a chance that there may be more non-standard structure. In fact, we don't know yet whether there are uncountably many distinct holomorphic structure. They have produced countably infinite. So we wanted to look at this question. So this is the question: does there exist uncountably many distinct holomorphic structure on each line bundle? Or rather, how do we characterize? So if you give me two holomorphic structure on ln, how do I characterize whether they are equivalent or not? So we needed a framework. So that I will proceed towards that. Just one remark here regarding the tensor product behavior. So this is crucial. The standard holomorphic structure, if you take on LM and on ln, you can form their tensor product. You will again obtain standard on the line bundle ln plus n. Same thing happens if you take standard and non-standard. But two non-standard structure, you cannot tensor product. So that is what is happening. So that means one has to look at the corresponding object, what is happening in the Picard group setting of CPQ1. Most probably this is no longer a group. So one has to dig the extra structure, what it is carrying. So, or some other exotic tensor, whether one can define in terms of two connections, so that two non-standard, again I can form the tensor to obtain another non-standard, something like that. Okay, so let me now proceed towards a framework where we can study this holomorphic structure, which gives an alternative viewpoint. So for that, I need to go to the sister algebra setting. So you look at the sister completion of the CPQ1, and you have the GNS space, sister completion of the coordinate algebra of the SUQ2. So this is the compact quantum group SUQ2, and you have the Hart state on that. Now look at the GNS space. Now at the algebra level, I had decomposition of this SUQ2 into all those ln's. So what I do, I take two L1 and L-1 only. Look at their completion with respect to this Hart state. That gives me two Hilbert spaces, H plus and H minus. You take their direct sum. So what happens? This C of CPQ1, the sister level, that is faithfully represented on this Hilbert space, H plus direct sum H minus. And then Dabrowski-Sitarz essentially constructed a Dirac operator 0 plus summable using this phenomena. So what you have first, you have this UQ SU2 actions. So in particular, these three generators E, F, K, they are going to act as a linear transformation from ASQ2 to ASUQ2. Now among these three, the K generator will act as algebra automorphism, and these two E and F, they will act as twisted derivation. And if you form this capital D by this phenomena, the 1, 2 and 2, 1 position, you put the E action and F action and compute the commutator, then you realize that the holomorphic and the anti-holomorphic, they are encoded in this Dirac operator. And this capital D induces the 0 plus summable spectral tuple on the standard codeless sphere. This was first discovered by Dabrowski and Sitarz, but this particular phenomena is very nicely explained in the Nesbev-2 set paper. So what we can do the following. So we can view the differential del bar as a closable derivation from this CPQ1, the coordinate algebra level, to to this Banach space bounded operators from H plus to H minus. Now, since this is a closable derivation, you can go to its closure. And what happens that closure, if I now equip with the graph norm, it becomes a Banach space. So this Banach space is going to play a crucial role here. Now, if I consider this Banach space in a different context, this compact quantum metric space setup of Riffel, Aguilar and Carr, they constructed a left inverse of this differential del bar. So what is that? This construction is a bit involved, so I'll just sketch the thing. So they constructed certain closed subspace of this Banach space BH plus H minus, and then you have a linear map which is denoted by integral simply because this is the extension of the Volterra operator. So it acts as the left inverse of the differential del bar. So that's why the notation integral. So this gives a map from X to the sister algebra of CPQ1. It's a bounded linear map. And it inverts the del bar up to scalar. So how does that scalar obtains here? So you have the standard picture of the sister algebra CPQ1. I can identify with the compact operators, direct sum C. So you have this psi infinity precisely the projecting everything to the scalar. So this formula, that is the unique character of this sister algebra CPQ1. So this integral precise relationship is integral of del bar x is x minus the scalar part. So this is inverting the differential modulo the scalar. So this is called the quantum integral. What we can do using this integral, so this is a technical proposition. This basically guarantees me certain maps landing exactly where I want them to land. So what we can do, we look at a particular Banach subspace inside this Banach space D. So this is a Banach space with the graph norm, not the sister norm. So inside this Banach space, you look at the Banach subspace, taking the intersection with the kernel of that psi infinity, the unique character. What you can do here, you can construct a family of maps via this prescription from H to H using this quantum integral. But these are not linear maps. If you look at the last factor, there is this del bar of H minus F. So unless that H minus F is scalar, so this is not going to vanish. So these are not linear maps unless H minus F is scalar. But H minus F scalar is not our concern because essentially we are going to look at the gauge equation. H minus F equal to scalar will give you the trivial gauge equation. So these are not our concern. So this map stays as genuinely nonlinear maps on this Banach space. Now, as we have already seen, but just quickly recall, I have the standard holomorphic structure on Lm. This is denoted by del bar n0. All the other holomorphic structures are given by this formula, where phi n was that twisted flip isomorphism. Our theorem is that if you take any random two holomorphic structure, del bar f corresponding to del bar f and del bar h. Now this f and h I am no longer restricting to any subalgebra. They can come from the entire ACPQ1. There is no restriction. These two holomorphic structure will be gauge equivalent if at least one family has a fixed point in the open unit ball of this Banach space H. So this is an if and only criteria. So that says in particular that solving the gauge equation is not going to be that easy because they are intimately related to existence of fixed points in some setup. So, but there is one advantage. So that means somehow if we can guarantee that there does not exist any fixed point, looking at this map, analyzing this map, I can immediately tell that the corresponding connections are distinct up to gauge equivalence. So they are going to give me different holomorphic structures on Ln. So that's kind of relooking the gauge equation in some setup where at least something can be done in terms of maps and or Banach space techniques or some other whatever, some Banach algebras techniques, whatever. So this is the possible direction that one can analyze now this fixed point existence to detect how many inequivalent holomorphic structure exist actually on Ln, whether countably infinite or uncountably many can exist. So of course, the line bundles one has to understand first in order to go for Grothendieck's theorem. So that was precisely our goal. So, okay, so this finishes the line bundle business for the moment. We'll again come back to it towards the end. Now I'll take a little detour to Atiyah class formulation. And we are going to see what is happening to line bundle again towards the end. Now, for the moment, this Atiyah class, this works beyond line bundle. This works in any holomorphic vector bundle over CPQ1. No restriction. Okay, strictly speaking, one can do this Atiyah class things in a bit larger setting, but little bit larger. But for this talk, I'll stick to CPQ1 only. So let's revisit the classical thing first. So if you start with a complex manifold X and look at a complex holomorphic vector bundle over it, smooth level connection always exists, but holomorphic connection may not exist. There is a cohomological obstruction. They are rigid. So that cohomological obstruction was studied long back by Atiyah in 1957, I guess. So Atiyah said that he obtained some cohomology class in the corresponding to the holomorphic vector bundle E over a complex manifold X. And he said this admits a holomorphic connection if and only this obstruction class vanishes. Okay, so this cohomology class directly generalizing to non-commutative setup may be a bit difficult. So instead we take the jet module setup, so which is equivalent in the classical case. What happens here, given the vector bundle E, you have the associated jet bundle, J1E, and this jet sequence is there. So what the Atiyah class is doing, this is the extinction class of this corresponding jet sequence. And the theorem of Atiyah was that holomorphic connection exists if and only this jet sequence splits holomorphically. And this is equivalent to saying precisely the obstruction class ATE vanishes identically in the holomorphic category. What we are going to do in NCG, now spaces are replaced by the algebra. So we have the algebra A. The differential structure is now the complex, the complex structure is precisely by this bigraded differential and the del and del bar corresponding differentials. And the vector bundles are finitely generated projective left modules. Okay, holomorphic vector bundles are equipped with del bar connection, which is flat, the curvature 0. CPQ1 setup, the flatness you don't have to bother, that is automatic. So first question is, what is the jet bundle in this setup? First, we have to tell what is in the smooth setup and then in the holomorphic setup. So the smooth setup, this was first discovered in 2023 by Majid and Simao, and almost simultaneously, I would say, by this Winder et al. So that appeared in 2025. We are not interested. They have talked about higher jet functors also. So we do not need that. We are in the connection setup. So we need to look at the first jet bundle only. So that we are denoting by JE10. So this is a linear direction. E is the given vector bundle over CP. Now I am in the CPQ1 setup, not general setup. So E is the given holomorphic vector bundle over CPQ1. You have the omega 10, you found the tensor product, take their linear sum. The left module, left action of the CPQ1 is specified by these two formula. On the E part, it is this AE plus the del A tensor E. So this precisely tells us that this direct sum is not a module direct sum. This is linear direct sum. The module action is the following. So immediately we have this sort exact sequence, which we are going to call it the Z sequence. So right now this is a sequence in the module category. Now, if you additionally assume that E is a vector bundle over CPQ1, so it is a finitely generated projective module. So that means what? This Z sequence is going to split in the smooth category, the the projective module category. So that means there will be a connection from E to JE10, but connection in the smooth setup. Holomorphic setup has not yet started, which is precisely our next target. So now if you assume E is a holomorphic vector bundle, so that means there is a connection. Can we say that associated Z bundle JE10 is also holomorphic? So what we need for that? Look at this picture. So we have the Z as a linear direct sum of these two. If I want to say JE1 is a holomorphic vector bundle over CPQ1, so I need to construct the connection del bar J somehow out starting with the connection del bar E. E is a given vector bundle over CPQ1. So that means I have to lift the del bar E to get the holomorphic structure on the Z bundle. That we do in 3 steps. So, okay. So let me directly open the picture. It will be, yes. So now del bar E is given to us. We are looking for del bar J. What we do first, this del bar E, you extend it to D tilde from this omega 10 space. This D tilde again will become a del bar connection. But if you simply simply combine these two connections, del bar E and D tilde, this is not going to give you a connection on the Z bundle. This is due to the module structure on the Z bundle. What you need is extra defect map, that is this beta E tilde. It's a map from this E to this space. Omega 01 tensor omega 10 tensor E. Now, if you define this map del bar J by this prescription, this beta E tilde is precisely the defect. What you can prove, this del bar J is the del bar connection on the Z bundle. The moment you have a del bar connection, flatness is automatic because we are in the CPQ1 setup. So this is going to induce a holomorphic structure on the Z bundle, starting from the holomorphic structure on E. But okay, so this is our first proposition, that this is indeed a holomorphic structure. But one has to prove something. If there are 2 holomorphic structures you are taking on E, but they are gaze equivalent. So essentially they are giving you same structure on E. Now you lift both del bar E and del bar E dash to the Z bundle. So you are going to get 2 connections now, del bar J and del bar J dash. Of course, you will demand whether they are also gaze equivalent or not. Otherwise, this does not make sense. But we have answered a bit more, from which it follows the construction, this lifting process, starting from the holomorphic structure on E to lifting it to the holomorphic structure on the Z bundle, this is actually functorial in the holomorphic category. So this is the endofunctor on the category of holomorphic vector bundles over CPQ1. Not only that, so that if you take maps between holomorphic vector bundles, so you are going to get nice commutative diagram which commutes. Everything happening in the holomorphic category, not just smooth category. Smooth category things are obvious, kind of. So as a particular corollary, this J15 map will tell you the previous question. If you start with 2 gaze equivalent holomorphic structure on E, their lift is also going to be gaze equivalent. So no problem is there regarding this lifting. Okay, so now what is the situation? Earlier our Z sequence was in the smooth category, smooth vector bundle level. Now we have lifted we have induced a holomorphic structure on the Z bundle. So this sort exact sequence now becomes a sort exact sequence in the holomorphic vector bundle category. So this is the sort exact sequence. We call it holomorphic Z sequence, not just in the smooth category. And the Atiyah class is obviously defined as the extension class of this Z sequence. Let me now propose the holomorphic connection over CPQ1. So what we are proposing, holomorphic connection over a holomorphic vector bundle E, del bar E over CPQ1. This is a left del connection, meaning 1-0 connection. It's a map from E to omega 1-0 tensor E. Now you have the holomorphic structure. So that means you already have a 0-1 connection, the del bar connection. Holomorphic connection, you are demanding as a del connection. You form the total connection, del plus del bar connection. So that is going to be a connection from E to omega, a map from E to omega 1 tensor E. So you look at the curvature. That curvature has to be 0. This is our proposal to holomorphic connection over a holomorphic vector bundle over CPQ1. The total connection should have curvature 0. With this definition, we have this satisfactory theorem. If you take any holomorphic vector bundle, then it will admit a holomorphic connection if and only if the holomorphic Z sequence is going to split in the holomorphic category. So that means the holomorphic connection exists over a holomorphic vector bundle over CPQ1 if and only if the holomorphic Z sequence will split in the holomorphic category. It always splits in the projective module category, but it has to split in the holomorphic category. Otherwise, you can take this also as a definition, meaning you state the holomorphic connection as the existence of the del connection for which the Atiyah Z sequence splits in the holomorphic category. Then you ask the question, can we characterize when the holomorphic connection? The characterization will be this particular definition, that holomorphic connection exists if and only if the total connection has curvature 0. So this was completely parallel to this Atiyah theory. Now over CPQ1, so one might guess what is the problem of extending it beyond CPQ1 at the moment. We could not do it because the main problem is in lifting the holomorphic structure from E to the Z bundle. So that is creating a problem. The moment you go beyond dimension 1, you have to show the flatness by hand. So curvature obstruction appears. So that is a problem at the moment. Maybe in future, we'll see. But right now, over CPQ1 setup, everything works very nicely. So this is an immediate corollary regarding the direct sum. So the whole holomorphic bundle is going to admit a holomorphic connection if and only each direct sum admits. Kind of an immediate corollary of this theorem. Now let me again come back to the line bundle situation. So line bundle over CPQ1, the standard holomorphic structure constructed was this del bar N0. Now in that paper, 2011 paper, the del connection was also constructed. In fact, the holomorphic structure they have obtained is essentially breaking the total connection into the horizontal vertical part. So associated to this holomorphic structure, I also have the del connection given by this formula. So now look at the total connection. They have also computed the curvature, which is precisely this. The presence of this Q number capital N now tells you that this total curvature is going to vanish if and only if n equal to 0. So that means this particular del connection, what they have constructed is holomorphic connection only on L0. It is not a holomorphic connection on other Ln. But there can be many other holomorphic connections. We don't know yet. This is not working, but something else may work. For that, we have this proposition. So if you invoke the SUQ2 invariance in the picture now, you demand the total connection to be SUQ2 invariant, then we have complete answer. Meaning the line bundle ln over CPQ1 is going to admit holomorphic connection if and only if n equal to 0. And this is indeed the case for the Riemann sphere. Classically, the Riemann sphere, only the trivial topological bundle O0 basically is going to admit holomorphic connection. No other n can admit. So we have the exact analog over CPQ1, but we had to invoke the SUQ2 invariance to conclude this. And the problem you can guess, I mean, because there are many non-standard structures. So to discard all those non-standard, staying with the standard, we had to invoke this SUQ2 invariance. But with this assumption, we have a nice satisfactory answer that only L0 is going to admit holomorphic connection, no other ln can. So this, of course, stays as a future question. So now you have many more holomorphic structure on ln. So what happens if you equip with non-standard structure? In particular, this will be very nice result if it turns out that some topologically non-trivial bundle are admitting holomorphic connection. With, of course, for standard not possible, with the non-standard. If it is possible, that will be a kind of a quantum phenomena, certainly no classical counterpart. So these are, of course, one for future. So there are plenty of literatures on CPQ1. So out of that, what we have chosen this particular 2011 paper, which was the introductory paper where they have induced the holomorphic structure on the line bundle. And then in 2025, this is the paper which constructs many other structures on each line bundle. And then this third one is that fixed point theoretic framework, which we have related with this Gauge equation and the fixed point framework on some Banach space, suitable Banach space. And this fourth one is that jet module thing, jet module and Atiyah class. Okay. Okay, thank you for listening.
Thank you very much. So do we have some questions?
Can I ask some questions?
Yes, sure,
Yes, please.
sure.
Okay, well, thank you, Guin. It was a nice talk. Okay,
Thank you.
Yeah, you mentioned this tensor product
Yes.
I'm trying to remember. I think you said two non-standard
Yes. Let me
things
just open.
cannot be two non-standard modules
Yes.
cannot be tensored, right?
Yes, that's what they have
Right.
said.
Yeah.
This non-standard paper, they have mentioned this
I
fact.
see, yeah.
That
Okay.
two non-standard. I believe Zhaoting may speak
Yeah.
in detail in the next
Okay,
talk.
right.
So that's why I have not gone through.
Exactly.
Yes, this
So
is the one.
So yeah, exactly. So that reminds me of a very similar situation in Hopf cyclic cohomology,
I
where
see.
you
Okay.
need when we introduced these anti-Yetter-Deniffeld modules in order to take cyclic cohomology of Hopf algebras with coefficients in some
Okay.
module. I mean, you cannot just take any coefficient, any module. I mean, there should be action, coaction, and some strange compatibility, which is the dual or anti-version of this Yetter-Deniffeld modules, which is very classic object, as you know, in representation of Hopf algebras.
Yes.
So
Yes.
in that case, the tensor product of these two anti-Yetter-Deniffeld cannot be made.
Okay.
So what happens that one Yetter-Deniffeld, you can tensor it with anti-Yetter-Deniffeld, and the result is anti-Yetter-Deniffeld.
Something similar is happening here also.
Yeah, something similar. Two Yetter-Denifelds, you can tensor, you get a Yetter-Deniffeld. So it's a bit like a supersymmetry. You know, it's only the case that two anti-Yetter-Deniffeld you can, and as you mentioned, I mean, it has to do with, of course, this the lack of a good definition of
Hmm.
pi 1, which is this Picard group. Of course, I mean,
Yes, yes.
so the Picard group, whatever it is, it's going to be very, very,
So
very.
it doesn't seem like it is going to be group.
It's not a
It has to
group.
be,
It's not
it's
a
not a
group.
group. It has to be
Exactly.
quantum
Yeah,
group or
yeah, yeah. It's going to
groupoid
be
or something.
something. It's going to be something very, very strange.
Yes.
That's right. Yeah. So, but I mean, it might be a good idea to investigate relation between these modules, non-standard modules or holomorphic things that was discovered vis-a-vis the idea of Jeter-Dinfeld and anti-Jeter-Dinfeld modules. So
I
for
see.
that, you just don't need, it's not enough to have an action. You also need a coaction. So there's a compatibility. So this has that kind of flavor to me. Is kind of maybe it's worth investigating. The second comment I have is, you see, yeah, indeed, this definition of holomorphic structure on modules as this, I mean, this decomposition that you have, this bimodular structure on forms and del and del bar and this thing. So, I mean, of course, in the case of, in commutative case, if you have a almost complex structure, you get this immediately.
Yes.
I believe, but I mean, okay, so it has to be seen. But as you know, in higher dimensions, almost complex structure is not necessarily a complex structure. There is
True.
this abstraction. There is this Nirenberg,
Yes.
whatever class. So it looks like that even in the case of for CP1Q, which is one-dimensional, maybe
Yes.
this Nirenberg theorem fails. So there are almost complex structures that are not that, because you mentioned, right? You mentioned that they're not necessarily equipped with holomorphic connections, but there is this sort of
Yes.
decomposition. I mean, so it might be worth looking at that as well. I mean,
Yes, I understood. I understood.
yeah, okay. So
I understood that.
this integrability issue, it might be something to look at. So,
Ah.
yeah. Okay. I mean, that's just
Can I ask one question?
yeah, for sure. Yeah. I don't.
So you mentioned this anti-Jeter-Dinfeld. So
Yes.
is there no tensor product which kind of works?
Well, we don't know. We don't know. We tried
Okay.
hard. We tried hard in these two papers. I mean, we don't know, but it looks like actually it's a kind of mirror image of Jeter-Dinfeld, and
Okay.
it doesn't work. Anything that you try to do, it doesn't work. And I believe, but we don't have a theorem that it doesn't work, but I believe one can even prove that such thing. No natural tensor product between them exists.
I
It
see.
should be, yeah. I mean, it has to do with this. This Picard group is not a group in this case for Hopf algebras.
Which is certainly not a group. It doesn't
It's
seem
not
like.
a group, no. But even
But it is not clear what structure it has right now.
yeah, it's not clear.
So
No.
it's not clear simply because you don't know how many holomorphic structures are there on
Yeah.
ML. So
Yeah,
that
exactly.
one has to look first.
Yeah, it's somehow, yeah, maybe it has to do with these higher structures. I mean, it's like categorical structures and this sort of things. So it could be
Maybe.
maybe a higher version of these things. But okay, so yeah, I haven't thought about this for a long time. I don't know. Yeah. Well, thank you. Yeah. So,
Are there
Thank
more
you.
questions from the audience?
Sorry, I was muted. I'm just wondering about the two non-standards. So what you're saying is you've got two bundles, then you've got two connections on them, and then you tensor them.
Yes. So you
What's
take ln and you
it's
take
flatness
ln.
that fails, is it?
No. You can. What is the if you form that tensor, that does not become a connection. flatness is not a problem on the CPQ1. Everything will be flat. If it is a connection, it is going to be flat.
Yeah, sure. Okay, I see. So you're missing the
So
bimodule map to allow you to flip.
Yeah.
So yes, the connection property itself fails.
Yeah. And these are, so it's not known if the non-standard ones are bimodule connections.
Sorry? So
It's
I was
not
going to
known.
say, it's not known. It's not known.
Yeah.
With the, standard tensor standard, you can easily form. That
Sure, yeah.
formula, if you are trying to apply non-standard tensor non-standard, it is not working. But there can be some other exotic tensor that we don't know.
Sure, yeah.
And Jyotting can
Okay.
say something maybe in this regard.
So the simple reason is the standard one is a bimodule connection. So if we have a bimodule connection, we can tensor it with a left connection, get another left connection. Non-standard ones are only left connections. So it's just like we cannot tensor two left modules. We cannot tensor two left module left connections. So that's the simple reason. But yeah, as they said, maybe there are some new definitions of tensor product and connection. So maybe they work in another
extra
sense.
twisted, maybe. Twisted kind of.
Twisted,
yeah. But not known yet, so speculation.
Yeah.
And can I ask another question?
More questions?
A very obvious question is like, what about extending this up to higher CPN?
Oh, that's important.
Flatness is the main problem. We are not able to live as of now to jet bundle. Sorry, you were talking about Atiyah or this setup?
No, I higher order CPS, so the quantum projective plane, quantum projective space.
Regarding non-standard structures?
Anything?
No, so there are two things. One is the Atiyah setup. Another is this non-standard setup. This non-standard setup beyond CPQ1 not yet done. Regarding the Atiyah setup, that I can tell you.
Yeah.
So we had to construct the holomorphic structure on the jet bundle. So we had to lift the existing holomorphic structure from E to J1E. So to lift it, we are able to lift, but we didn't check the flatness because we never, we didn't have to check the flatness because it was automatic. It's a CPQ one.
Yeah. But I mean, the flatness can be, so in this case, if I've understood what you're saying, so you're working in the covariant case, equivariant case, OQSUN, equivariant.
Okay.
So then because flatness is basically a left B module and a co-module map at the same time, you can bring it across under this equivalence, Takeuchi's equivalence as it's known, to a statement on the finite dimensional, like on the analog of the fiber. And then it turns into a question of representation theory. And a lot of the time you can just answer it directly from representation theory. So that should be doable.
That should be doable. So this is exactly what we are doing now. So we are looking at it. So it was very recent paper. So the CPQ one we have finished. So the higher version we are looking at right now. So otherwise this flatness checking by hand is going to be very difficult. It's a massive expression. So one has to invoke the representation theory.
Absolutely, But then it should be almost immediate. Well, okay.
Not yet finished. Well, not yet finished. So
not yet finished. Okay.
Yeah.
Do we have more questions?
Just one more comment. I mean, I think if I remember correctly, I'm not sure. Describing holomorphic vector bundles on higher projective spaces is a highly non-trivial matter.
Yes.
So when you go to CP2 and CPN for n bigger than equal to 2, it's an extremely difficult matter. It's been done in some cases, low dimensional, but I think in general it's not. Oh, there is the name of Horok comes to mind, and Atiyah and Hitchen used the Horok's construction to construct instantons on four-dimensional flat space, well, a sphere basically. This is the ADHM instantons. describing them is very, very, very delicate problem. So the quantum case, I don't know. I think if you really insist on holomorphicity, it could be quite delicate. I don't know. I think maybe, but yeah.
It's reason. I mean, once the line bundles are equivariant, it's really not that bad. Again, just like I said before, you can turn it into.
You're right. I mean, at the smooth level is not a problem. This is the describing the complex structures. I believe there is moduli in that case. You see,
in the classical case, probably, yeah.
Yeah, in a two-dimensional case, you have a moduli of holomorphic structures on each of these holomorphic bundles. Rather than, but as Guin said, it's rigid in the classical case in CP1, but it's not rigid. There's a continuous moduli. So, yeah, that's.
But just to say again, like once you introduce equivariance, everything becomes much simpler.
Yeah, smooth, I believe, it's much simpler, but holomorphic could be very difficult. But okay.
So we have time for a quick, urgent question. Yeah. If someone has one of these, feel free to ask it.
Yeah.
Any from?
Otherwise, let's thank Satyajit for a great talk. Thank you.
Yep.
Thank you. Thank you all. Thank you.
I think there was a question from Prague. Sorry, I was too quick. Right?
Yeah. No, I was just asking if there were any, but it doesn't seem like it's. So
then, yeah,
we're good.
Thank you.
Yeah.